Okay. Uh, so sorry about not having a in-class type of lecture today, but for one thing, my plumber didn't actually get here on Thursday. He is coming today, and so I had to deal with that today. And most of us aren't going to be there in class, so I figured, let's have a recording instead. So there's really just not a lot that I want to show you today about what we're going to be getting into with functions, and that is composition of functions. And it's pretty useful, pretty powerful, but it's not very complicated. So you know how, like if we have this function here, f of x. Again, f is the name, f of x, this part right here, just tells us that the function is dependent upon x. So when we plug something in for x, it changes the value of y. So again, the function is dependent upon x. So for instance, if I want to plug in something in here like x equals 3, then, and forgive me, I'm on a mouse today, we plug in 3 to our function, we get something like 2 times 3 here. So we do that calculation, we do whatever the function is telling us to do. So of course 2 times 3 is 6. So we would say that f of 3 equals 6. And like I was saying on Monday, if we have something that looks like this, f of some number equals a particular number, what this is really a coordinate. So this right here is our x portion. It's what we plugged in for x. And when we use x, what we get out for y is 6. Okay, so this would be our x coordinate and our y coordinate. But again, this is what we know how to do with these functions so far. We know how to plug things in. We know how to graph them. Okay, nothing too crazy. But I want to reiterate something that I have said before, and that is that functions are like little machines. So you can imagine, you plug something into a machine and you get some kind of output. So like for instance a car, you put gasoline into a car, and when you use that gasoline it results in forward motion or backwards motion. Cars can go both ways. But the thing is, you're plugging something in, you're giving it some kind of input, and it gives you an output. Now, these are not like cars as much as they are like maybe an engine or a transmission. Okay? Now, you have to be able to put these things together in order to actually get our full functioning automobile. Okay, so we can actually do what's called a composition of functions, compose one function of another one, and get a completely new function. Okay, so for instance, I've got f of x and g of x here. F of x is 2x, and g of x is 1/4 x. So I can compose these two together, and what that does is it kind of like meshes them, and it meshes them in a particular direction. So let me use f of x first for our base function. What I'm going to do is I'm going to compose f of g. So that is f composed of g. That little circle there means composed of x. And what this means is that I'm going to take g of x, whatever I have for g of x, and plug it in for f of x. So this right here, whoops, let me try that again. This 1/4 x is going to get plugged in for x. So if we do that, of course this one starts out 2x. So what I'm going to do is I'm going to write 2x, but instead of writing an x, I'm going to open up parentheses, because I know that I'll be plugging things in to x, and I know that when I plug something in for a variable, I need to use parentheses to do that. So this part's going to get right here where the x is. Okay. And now, of course, we can do some simplification. I need to multiply this 2 times 1/4 x. Okay, well, 2 times 1/4, that's 2 over 4, and that gives me 1/2. So f composed of g of x, at least in this case, we get that that is equal to 1/2 x. So like I said before, we've got these two parts that we have that we're putting together to make one whole machine. And when we put them together, it gives us a totally new machine. F of g is equal to 1/2 x, where the other two were either 2x or 1/4 x. Now, like I said before, I mentioned this, it does it with direction. Okay, so the question is, will it be the same thing if I do the other way around, if I compose g of f? Well, let's see. So I'll go ahead and back this up. And now I'll compose g of f. I'm going to go the other way around. I'm going to take this part right here and plug it in for x right there. Okay? So now I have g composed of f of x. So remember, g composed of f is the name, x is what it's dependent upon, is equal to, okay, this one says 1/4 times x. So 1/4, and I'm going to open up parentheses because I know I'm going to plug something in for x. I'm going to plug in 2x. It's an odd 2. Okay. So once again, we need to simplify this and see what we actually have. So 1/4 times 2x is the same thing that we were doing the last time. And so, yeah, in this case at least, g composed of f comes out to be the exact same thing as f composed of g. They both come out to 1/2 x. Okay. So now the question has to be, all right, if this worked, if these gave us the same thing, no matter which way we plugged it in, f composed of g or g composed of f, if they come out to be the same thing, does that happen all the time, no matter what functions we have? Okay, so let's see what happens if we change our functions. And instead of having x times something in both of these, let's change the function so that we have x maybe minus something. Let's say x minus 3. Okay, well, let's see what we get. So we'll do f composed of g first. So we've got f composed of g. Vector went weird. Of x. And once again, like I said, if we are composing f of something, then we're going to start with the framework of f. So this is going to be 2x. And we know we're going to plug something in for x, so we're going to replace it with parentheses, and that's going to be x minus 3. So let's see what we get. Well, we got to distribute this 2 into here. So 2 times x is 2x. And then 2 times negative 3 is negative 6. And so we get that f composed of g of x gives us 2x minus 6. Okay, so let's keep that in mind. Let's keep this on the board too so we can compare and see what happens when we replace this with g composed of f. So let me split this here. Again, we're going to do g composed of f now. So that means that we're starting with the g framework, x minus 3, but we're going to plug in the f part into x. So again, we're going to open up parentheses for x, plug in 2x, and then we have the minus 3. Okay, well, simplifying this one, we don't need those parentheses because nothing's acting on it, nothing's multiplying out here, nothing's raising it to a power, so we can get rid of these parentheses. And now we have G composed of F. Try that F one more time. Of X is equal to 2X minus 3. Okay, so yes, indeed, F composed of G and G composed of F in this case happen to be different. Okay, and it really depends on what you're doing in the real world. Okay, so each of these components is going to have some kind of real world connection. So we have to kind of like remember order of operations. We need to remember, you know, what are we actually trying to do with these numbers? What's the process as to which one goes first? And we'll get more into that when we get into some word problems. But again, I want you to remember that F composed of G and G composed of F, or whatever way you are composing functions, the directionality matters. So this one is not the same as this. Obviously, this is 2x minus 6 and this is 2x minus 3. Okay, let me clear this real quick. All right. Now, what about if I do the opposite? So this one is 2x, right? This is f of x equals 2x. This one, what if I do the opposite of this one? Maybe instead of having 2 times x, I have x divided by 2. Okay, so let's see what happens when we compose functions that have opposite operations. So again, I'll do f of x first, f of g. We're starting with this framework. So we're going to have 2 times x, and then when we have that x, we're going to plug in this part. Okay, so we're going to plug in x over 2. Okay, well, you can probably see what's going to happen here. I've got x divided by 2 and then times 2. This is just like when we're solving and trying to cancel things on our sides to get x by itself. Multiply by 2 and divide by 2 cancel, and we are left with just x. Okay, but like we saw with the previous example, that directionality matters. So let's see what happens when we plug it into the other one as well, and do g of f. So g of f, and that's a weird f, f of x is equal to, okay, we're starting with this framework this time, so I've got a fraction. I'm going to plug in 2x for x over 2, and we've got the same problem. We were multiplying by x here. I'm sorry, we're multiplying by 2 here, but dividing by 2 here, again, that's going to cancel and leave us with g composed of f of x is equal to just x. So what does this mean about these two functions? Well, like I said when I started this example, these are opposite operations. This is multiplying by 2, this is dividing by 2. These are inverse of each other. In fact, we would call g of x or f of x, whichever one we're starting with, we'd call that an inverse of the other one. an inverse function. So another way we might write this is actually f to the negative 1 of x. Remember that when we have that negative power 1, it just means flip it. Well, flip it is another way of saying inverse. So we're saying here that f to the negative 1 of x, that means that this is the inverse of this one. They're related by being opposites of each other. And what we just did here by finding that it comes down to x, both of them come down to x, is proving that they are actually inverse. So anytime that you compose two functions of each other and both of them come out to be just plain old x, that means that they are both inverse of each other. Okay. So let's back all this up. Let's say I've got something like this. 3x plus 2. F of x equals 3x plus 2. Let's say that I want to find the inverse function of f of x. Now I don't have another function to compare it to. I can't compose these functions because there's only one of them. So how do I find this inverse function? Okay, well, again, an inverse function is the opposite of what this function does, and it does the opposite in the correct order as well. You know, I'd have to subtract the 2 and then divide by the 3. I couldn't divide by the 3 and then do other things. It'd get messy. So we want to make sure it does it in the correct order. We want to make sure it follows all that, but does it in the opposite. So what we're going to do is we're going to first say, well, f of x, that's kind of hard to write. Let's just change it to y. Because after all, f of x represents, like I said, the y part of a coordinate. So we've got y equals 3x plus 2. Now, again, because I want to do the opposite, what I will do is I will now flip the positions of x and y. So x is going to go here, and y is going to take its place. Now what we want to do is we want to get back to the point that we have y by itself, that we have y solved for. So we're going to need to, of course, get rid of this positive 2, so we'll subtract 2 from both sides. That cancels, that gives us x minus 2 is equal to 3y. Then we need to get rid of that 3, so we'll divide both sides by 3. And we get a new one where y is equal to x minus 2 is all over 3. And then we can change this back to a function by changing y into f of x. But remember, this is the inverse function, so we're going to call this f to the negative 1 of x. Again, this is the inverse of f. Okay. But, of course, sometimes I mess up. So let's make sure that this is actually true. Let's make sure that I've actually found the inverse function. So I'm going to compose these of each other, and again, if I get just plain old x, if there's nothing left but x, then these are indeed inverses of each other. So I'll compose f of this, f composed of, we'll say f to the negative 1 of x is equal to, okay, so we're using f as our framework, so we have 3, then x, I might have to get rid of that. I'll just back this up a little bit. Okay, f is 3x, so we have an x here. We're going to plug in this part, x minus 2 over 3, and then we add 2. Again, this is the exact same thing as this, it's just instead of x, we've plugged in this inverse function. So let's see what happens. Well, first thing I see going on here is that I've got 3 times something that's being divided by 3. So since we're dividing this thing by 3 and then multiplying by 3, well, that cancels. So f composed of the inverse is going to be now just x minus 2 plus 2. Well, I mean, obviously right there, negative 2 and positive 2 are also opposites. They're going to cancel. And we do indeed get just plain old x. By the way, if you don't know what these marks mean, it means same thing that was above. So the 2 little lines just mean that again. Okay, so this is pretty strong evidence for this indeed being inverse, but to make sure, let's do it both ways. Not just f composed of the inverse, but the inverse composed of f. So again, I'll erase this real quick, and we can try that out. We'll switch the direction here. So now we're using this as our framework. We have a fraction here. We've got x is going to be this thing right here, 3x plus 2. And looking at it, we actually don't need those parentheses. And then this negative's right here over 3. Okay, so again, here I see positive 2 and negative 2. Like I said before, those are opposites, they cancel. So now we have 3x over 3. Well, we're multiplying 3 times x here and then dividing by 3. That means that, again, that cancels, and we are left with just plain old x. So, indeed, these are inverse of each other. They are doing the exact opposite of each other. And it's in the opposite direction. So, again, we can prove that these are inverse by composing them of each other. Composition of functions is very useful. And you can imagine using the machine simile that this, if it's a machine, and if this is a machine that does the opposite, then when you put these two machines together, they're just going to cancel each other. You can think of it like this is a screwdriver that is going in the forward motion. This one's a screwdriver that's going the opposite. It's backing the screw back out. If you put these two things together, well, that screw's not going to go anywhere, is it? Okay, so once again, composition of functions is very useful. Our functions are already like machines, but sometimes those machines are just small, they do one very specific thing, and we need more things to come in, plug into those things, and do some more operations for us. Okay? So again, quick lecture today. I don't think this is going to be too terrible for us to pick up. I'm going to lecture about this again on Monday. It'll be pretty small. But then after that, we're going to be getting into some other territory with functions. Okay, so I hope everybody has a good weekend, and I will see you on Monday.